Hello everyone and welcome. In this video, we're diving into the fascinating world of game theory. We'll explore the fundamental concepts, understand how strategic decisions are made, use game trees to map out possible outcomes, and learn about the Minimax algorithm, a powerful tool for making optimal choices. So, what exactly is game theory? At its core, game theory is the study of mathematical models that describe strategic interactions between intelligent and rational decision-makers. It's about understanding how individuals or entities make choices when the outcome of their choices depends on the choices of others. There are four key components of game theory. The first one is players, who are the entities making decisions. Second, strategies. These are the possible actions that players can take. Third, payoffs, which refer to the outcomes resulting from different combinations of strategies. And fourth, rational behavior, which suggests that players will make decisions to maximize their gains. Game theory is used in various fields, including economics, artificial intelligence, psychology, and mathematics. It helps us analyze and predict behavior in competitive situations, from simple games to complex real-world scenarios. Games can be represented in different formats, each highlighting specific aspects of the strategic interaction. We'll discuss two common formats: normal form and extensive form. Normal form is also known as strategic form. It represents a game as a matrix, displaying the payoffs for each player based on every possible combination of strategies. In the normal form, all players are assumed to make their moves simultaneously. Look at the example in the matrix. The rows represent player 1's strategies, up or down, and the columns represent player 2's strategies, left or right. Each cell shows the payoffs for both players. The first number in the cell shows the payoff for player 1, and the second for player 2. On the other hand, extensive form represents a game as a tree structure, showing the sequence of possible moves and the information available to each player at each decision point. It is very useful for games where players make moves in a specific order. In the example shown in the diagram, player 1 has two strategies, up or down. Depending on player 1's move, player 2 gets a turn and chooses between left or right. The numbers in parentheses show the payoffs for both players at the end of each possible sequence of moves. Game trees are visual representations of sequential games. These trees show all possible moves and the outcomes that result from those moves. Let's explore the key components of a game tree. Nodes represent game states or decision points in the game. Edges represent the possible moves or actions that can be taken from a particular node. Player nodes indicates the player who makes a decision at that point in the game. Chance nodes indicates the random events with associated probabilities. Terminal nodes represent the final states of the game, along with the payoffs for each player. The diagram illustrates a game tree. Here P1 means player 1 and P2 means player 2. Player 1 starts at the root node and chooses a strategy A or B. Then player 2 gets a turn. Finally, player 1 plays again. The terminal nodes show the final payoffs that each player receives at the end of the game. Let's look at a practical example of a game tree tic-tac-toe. Here we have a simplified game tree that shows the first few moves of tic-tac-toe. Because of symmetry, we only show the unique board positions. The root node represents the initial empty board. Player X starts by placing an X in one of the positions. Player indicators on the node show whose turn it is to play. At level 1, player X has made the first move, and there are three possible unique positions on the board. It can be at the center, at the corner, or at the edge. After this, it is player O's turn to play. Level 2 shows a few possible responses by player O, depending on the moves of player X. Note that the tree expands exponentially. The complete tic-tac-toe game tree contains approximately 255,168 terminal positions. The Minimax algorithm is a decision-making algorithm used in game theory to find the optimal move for a player, assuming the opponent is also playing optimally. The goal of the Minimax algorithm is to maximize your minimum gain or minimize your maximum loss. It's a recursive algorithm that evaluates all possible future game states. This algorithm works for games where both players can see the entire game state, that is, perfect information games. It has real-world applications like in chess, checkers, tic-tac-toe, and Connect 4. The key principles of Minimax are as follows. The maximizer tries to get the highest score. The minimizer tries to get the lowest score, and decisions are based on evaluating future moves. The first step in the Minimax algorithm is assigning values to the terminal nodes, also known as leaf nodes in the game tree. First, we identify all terminal positions where the game ends. Then we assign utility values to each terminal position from the perspective of the maximizing player. Higher values represent better outcomes for the maximizing player. Conversely, lower values represent better outcomes for the minimizing player. Common values are win, which means +1, loss, which means -1, and draw, which is 0. In the illustration, all the terminal nodes have been assigned utility values. The numbers inside the rectangles represent the utility for the maximizing player. After assigning values to the terminal nodes, we propagate values upward through the tree based on the objectives of each player. At the maximizing nodes, we select the maximum value from the child nodes. At the minimizing nodes, we select the minimum value from the child nodes. We propagate these values all the way up to the root node. At the root, we choose the move leading to the highest value. This assumes that both players make optimal decisions. For example, in the illustration shown, the values are being propagated upwards, finally leading to the root node. The optimal path, which is the sequence of moves that leads to the best outcome for the maximizing player given the opponent's optimal play, is highlighted. Here's a simple implementation of the Minimax algorithm in Python. The function Minimax takes the current game state, the depth to which the tree should be explored, and a Boolean indicating whether the current player is maximizing or minimizing. The key components are the following. This is a recursive function, meaning it calls itself to explore the game tree depth first. The player toggle alternates between maximizing and minimizing players. The base case returns an evaluation when reaching terminal nodes or maximum depth. In the maximizing step, the function selects the highest value from the child nodes. In the minimizing step, the function selects the lowest value from the child nodes. The evaluate function assigns scores to board positions. Finally, the function get_children generates all possible next states from the current node. Minimax algorithm has numerous real-world applications. It is implemented in board games such as chess, checkers, and Go. It forms the foundation for artificial intelligence opponents in perfect information games. For example, the Deep Blue chess engine used Minimax with alpha-beta pruning to defeat world champion Garry Kasparov. It is also used in game theory to analyze competitive scenarios where multiple agents with conflicting interests make strategic decisions such as in economics, military strategy, voting systems, and market competition models. Minimax principles are incorporated into advanced reinforcement learning algorithms for competitive environments. For example, AlphaGo combined neural networks with Minimax-based tree search to master the game of Go. It is also used in decision-making and adversarial scenarios to make optimal decisions, considering worst-case opponent responses such as in automated negotiation systems, security applications, and resource allocation. It also powers artificial intelligence opponents in mobile strategy games, providing challenging gameplay without requiring internet connection such as in chess and checkers apps, as well as original strategy games with turn-based mechanics. There are advanced variations in Minimax algorithms such as alpha-beta pruning, expect-to-minimax for games with chance, and Monte Carlo tree search. Alpha-beta pruning can search game trees much faster by eliminating branches that won't affect the final decision. If you like this video, hit that like button and don't forget to subscribe. Visit codelucky.com for more such useful content.